पता चला कि
हेलो।
छोटी पोस्ट मिलता हेलो। हेलो। कैमरा नहीं आ रहा भाई, इनको एक्सेस दो भाई कैमरा को। राले वन की एक्सेस राले। ओके ओके, चलता कोई बात नहीं। एक्सेस राले राले। वन
Karthik sir, good afternoon, Karthik sir. Can you, Karthik sir, Karthik sir, please confirm. Can you hear the voice?
Hello? Hello?
Good afternoon, Karthik sir. Can you hear me?
Yeah, I can hear you.
Sir, your voice is low. Please verify once. Sir.
I don't know. Can you hear now?
Yeah, yes, sir. Can we start, sir?
Yeah.
Yeah. Thank you. Sumit sir, please good to go. You can start.
Shall I share my screen and start?
So 1 minute, sir. Sumit sir, our personal introduction, please, for 5 minutes.
Hello. Hope my voice is audible. Dr. Asif sir, please confirm.
Yeah.
Or Madhukar sir to please confirm. Okay. So good afternoon, everyone. Welcome to the second day of our faculty development program. I'm glad to see you all ready to dive deeper into the topics and discussion with the 6 days virtual national level faculty development program on emerging research paradigms, methodology, analytical tools, and AI integration in collaboration with IMEC and Professional Education Services. Today, we have our guest, Dr. G. M. Karthik sir. Dr. G. M. Karthik sir is an assistant professor in the Department of Mechanical Engineering at the Indian Institute of Technology, BHU, Varanasi, Uttar Pradesh. Before his current role, he served as a research assistant professor at Pohang University of Science and Technology in South Korea. His research primarily focuses on additive manufacturing and materials. Joining Dr. Karthik is the recipient of several prestigious awards fellowships, including the Brain Pool Fellowship, Academic Fellowship, Well Specialty Award, Sudarshan Bhatt Memorial Award, Academic Proficiency Award, and the Shastri Institutional Research Collaboration Development Grant. His scholarly work is well recognized with over 40 journal articles in internationally reputed journals and at many international conferences. We welcome you, Dr. G. M. Karthik sir, and I request you to please go ahead with your presentation today. Thank you.
Yeah, thank you for the introduction. I'll share my screen. Is my screen visible?
Yes, sir.
Yes, sir.
Yeah. So, today I'll be talking on the use of AI in the area of metal additive manufacturing and when you are designing some new alloys. So this is some of the work that I recently started doing. My expertise is in the area of additive manufacturing and materials joining and alloy design and things like that. So I'm trying to incorporate AI into these processes. Okay, so I'm not sure how much of you are aware of this metal additive manufacturing and alloy design and things like that, because I understand that faculties from all domains or all departments are involved in this, not only from mechanical and things like that. So what I thought is I'll first introduce about metal additive manufacturing very briefly, and then I will explain how we are integrating AI into metal additive manufacturing. Is it okay, or if you are very comfortable in metal additive manufacturing, then I'll straight away jump to AI. Can somebody say?
Sir, I think if you can introduce about metal additive manufacturing, it will be more better.
Okay. So with that context, so I'll first give you an idea of metal additive manufacturing. So you would have heard about different names for this process. People would have called this process as rapid prototyping, rapid manufacturing, 3D printing. All these words you would have heard, or you would have read, or you have seen a news article, something like that. Okay, this process is called with different names in different groups or context. Whenever based on the context, these process is called with different names. The first name which was started for giving to this process is rapid prototyping. So when so the main idea of this name is you can make prototypes. So let us assume a car manufacturer is there, and he has a new design of his car. So before manufacturing this whole thing, he wanted to check how the design is, whether the design looks okay, not okay, is it aesthetically good. To have a flavor of how the design is, people use this technology to make those prototypes. So it is just a prototype of the real car. So it might be in a much smaller scale. The size of the car may not be the size of the prototype, may not be of the size of the real car. It is a prototype with a much scaled down version based on case to case basis. Okay. So since we are able to make prototypes rapidly, so there is a question comes here, uh, why prototype manufacturing, why you call it rapid? Because if I wanted to make any part, either you need to, if it is a kind of a sheet metal operation, if you see your car body, most of your car body items are sheet metal. So they're all of 1 mm thickness, less than 1 mm thickness sheets, and they are formed into a particular shape. So if you want to form a particular sheet into a shape, then you need a die to form it to that particular shape. So first, if you wanted to manufacture a car body outer frame, first you need a die of that particular outer frame. So making this die itself is a very big task, because you need to invest a lot on making this die. Once the die is over, then you can make this shape of car part that you wanted, that outer frame part, let us assume. So this is the bottleneck. First, you need to design a die, and that die itself, die making itself has its own lead time. And then once the die is made, then you have to stamp it into a particular shape, or you have to form the sheet into that particular shape, and that also has a lead time. So if you wanted to make a prototype, you need to invest a lot. You need to first manufacture these dies, and you need a subcontractor to do it, and things like that. So one is lead time and another one is cost. So to avoid this, people thought of using this rapid, or using this technology for making these prototypes rapidly. The context of rapid here is compared to the conventional way. The context of rapid is not to say that you can quickly make. Okay, it is in the context of, in one case you are making 3 days time, in another case you are making in 1 day time. So that is the context of rapid here. It is not that the process gives you parts quickly. In comparison with another process, yes, it will give quickly. So that is how the rapid prototyping comes into picture. And then you have rapid manufacturing. Then people thought, when we are able to make prototypes, why can't we make and used parts? Why can't we manufacture parts so that it can be used in service? Okay, so then rapid manufacturing started becoming very popular. People started calling this technology as rapid manufacturing compared to prototyping. But the main problem with these two terms is the word rapid and manufacturing. There are other technologies also, because I told you this word rapid is related to an X process. Okay, if I am so this rapid manufacturing, there are other rapid manufacturing techniques also. So this is kind of a misnomer, like whether we are trying to explain about additive manufacturing or it is like some rapid manufacturing. This also comes under rapid manufacturing, but it doesn't really explicitly mention I am developing materials through this technology, additive manufacturing. So people started looking for a new term to explicitly mention this. Okay, so let us assume when you compare simple casting and investment casting. Okay, investment casting might be rapid compared to simple casting. So this rapid term is becoming very kind of not really explaining the process. So people started looking at a new term and they come up with this solid freeform fabrication. So here the context is to say that you can make solids of any shape, any size, and you can fabricate it. So this is solid freeform fabrication. And then people also thought we can make tools rapidly. So rapid tooling has come into picture. Then this 3D printing has become very popular, where people like you have a 2D printer, you have a printer in your office where you print. So it is just one, there is no third dimension to it. But if I'm printing the same letters in the third dimension also, one over the other, one like print and again print on top of it, again print top of it, again print on top of it, same thing. And if you have that building on top, if your printer can allow you to build one over the other, same letter, then you will have the three dimensions of that particular letter. So that is what people started calling it as 3D printing. So 3D printing has become very popular. I think you would have heard this word. Definitely everybody would have heard this word in, because it has become very popular in the media. Okay. But 3D printing, although the name is interesting and became very popular, it is one of the process of additive manufacturing. 3D printing is also a process. It is not a technology. So whether if somebody says 3D printing, whether he is talking about that particular process of 3D printing or he is referring to the technology of additive manufacturing, there is a confusion. So that's why people, ASTM has come up with this terminology called additive manufacturing. So because in additive manufacturing, you are developing materials layer by layer, like one deposit one layer and on top of it deposit another layer and on top of it deposit another layer. So you are building the component by adding materials one over the other. So that's why it is called additive manufacturing. So if you are referring to this process, you have to refer it to as additive manufacturing in the current context rather than any other words. Additive manufacturing is the terminology for this particular process. Okay, so this is the history of how this name has come. Now this alloy design is something that everybody knows. So there is always an interest of developing high strength materials. Okay, the world is continuously looking at materials which have higher strength, higher ductility. So you wanted a strength ductility trade-off, because you all know that when you increase the strength of the material, the ductility drops down. So you need a material whose strength is high, but the ductility is not very bad. Ductility also should be reasonable. Okay, so there is always this research direction of alloy design is never ending. Okay, because you have so many elements in the periodic table, so you can take any combination and you can also take any fraction of this element into your alloy. So which alloy will work, which alloy will not work is a kind of a ocean of possibilities are there, infinity possibilities are there. So you need to come up with a composition which works. So at that time AI ML will work for you. So we have done some work. I will just present what we have done. Okay, so this is what I am trying to say. This is formative manufacturing. So simple casting. So you basically have a pattern and then you remove this pattern, and that pattern will be the shape of the component that you wanted to use. And then you melt your material that you wanted to make the component of, and then fill this pattern with that particular material because it is in a liquid state. And this material will solidify and then you will have the final component. This is formative manufacturing, which is like casting. Then you have subtractive manufacturing. If you wanted this shape, you can start with a block like this and then machine wherever it is required, and then you end up into this particular shape. The main disadvantage with this process is you are wasting all this material. You started with this You removed all this material, and then this is kind of subtracting. You are subtracting material, and then you are able to achieve this particular component. Okay. And then here is additive manufacturing. If you wanted this shape, what you do is wherever material is required, you only deposit there. So in this particular region, you need material, so you only deposit there. And then till here, you need material, and you only deposit there. And then you want material only here, and then you deposit here. So here we are actually developing this component by layer material addition at specific locations wherever material is required. So with this, what happens is you are able to develop complex shapes, and the main advantages with this technology is you don't have separate tooling. So in casting, you need to make this mold, you need to make this pattern, and then the whole things which are required for casting has to be done. These are all separate tooling. These are not part of your component. This is a tool, this is a tool, this is a tool, this is a tool. This is your component. So to make this component, you need all these tools. And in the same case with manufacturing, in subtractive manufacturing also, you need some machining cutting tool to make this. So there is also a tool involved in this. But in this additive manufacturing, you only require a deposition head. Okay, you are depositing material wherever it is required, and this particular thing is actually helping you to fabricate complex near net shaped parts. Okay, so if I wanted another shape other than this, I need to make these tools separately. I need to have a different tool set for if I wanted to make this. Even in let us assume, even in kind of subtractive manufacturing, there are some things that you can do with milling, some things can be done with turning, something can be done with grinding, something can be done with super finishing and things like that. So different operations, different tooling. But in additive manufacturing, it is agreed upon that you can make near net shaped components. Okay, and so separate tooling or machining is not required. But the major disadvantage of this technology is you don't get dimensional accuracy and what do you say, surface finish requirements, what you can achieve through machining. In machining, you get the best surface finish possible and the best dimensional tolerances that you wanted. But in additive manufacturing, you are not very close to this, but you are better than the subtractive manufacturing, but you are not very close to machining. So some post processing is required. Okay, and that is one direction where a lot of research is required, where which process to be used, because you are already making a complex shape, and how to machine that complex shape. Okay, if you wanted to improve the surface finish and things like that. So that is one of the disadvantage in additive manufacturing. Otherwise, you can form whichever shape that you wanted, because there is no separate tooling and specific for that process. So any shape you want, you can easily make if you don't have separate tool requirements. Okay, so there are several technologies developed for additive manufacturing, from stereolithography, fused deposition modeling, 3D printing. So like this. So this is the invention. So you have first invention from in 1981. This process is invented in 1981 in Japan by Nagoya Municipal Industrial Research Institute. And then subsequently, there are significant number of processes evolved in additive manufacturing. So the initial first three things, that polymer of VAT photopolymerization, material extrusion, material jetting. Predominantly, these technologies are used for polymers. And then you have technologies like direct energy deposition, powder bed fusion, sheet metal lamination. They are all used for metals. Okay. So I think most of you know, in additive manufacturing, initially you need the CAD model of the part that you wanted to print. If you wanted a shape of a cup, first you need a CAD drawing of this cup, and then this CAD drawing will be converted into an STL format. Basically, you are converting this model into a surface. So you are creating two surfaces. You are basically changing it into surface, and each surface is indicated by several triangles. So this is STL format, and this particular format is what most additive manufacturing machines understand. Okay, and then you upload your STL file to the machine, and then you do the machine setup, like what should be the process parameters to use, whether this is support structures and things like that, and then you print the sample. Once you print the sample, you remove the sample, and then you do some post processing. I told you that some machine cleaning or some small machining might be required even in additive manufacturing, and then you use a final component. So these are different steps involved, and what happens in each step is what is indicated here. Okay. So as I told you that I will introduce to metal additive manufacturing technologies. So these are metal additive manufacturing processes. So based on the raw material, so let us assume I wanted to make a component of stainless steel. So based on the raw material that I want use, so or the morphology of the raw material that I use, if I have stainless steel powder, then there are technologies which are based on powder. If I have stainless steel wire, then I have technologies based on wire. If I have stainless steel in the form of a sheet, then I have technologies for additive manufacturing if they are in the form of a sheet. And if I have technologies in the form of a plate, which are slightly thicker, like 3 mm, 4 mm thickness. Sheets, I mean by 0.1 mm, 0.2 mm, less than 0.5 mm. And then in the case of sheet plates, I am talking about more than an mm thickness. Then you have technologies like it. So based on how you take your raw material, you have to choose different metal additive manufacturing technologies. And also when you take powder, whether I am melting my powder completely when fabricating, then you have technologies which involves complete melting. And if I am not melting my powder fully, I am only melting the surface of my powder. When it is required, let us assume your powder is having a very high melting point. Okay, so your laser power or the heat source that you need to give to achieve the temperature will be very high. Like you need a very high power laser or a high, so it is very expensive. So people thought, why can't I melt only the surface of this powder and then bond it? So there are technologies which uses partial melting. Only the surface of the powder gets melted. Like in the case of very highly conductive materials like copper. So if you have highly conductive material, it's very difficult to contain heat at that particular region because of the conductivity, very high conductivity. Okay. So you will only end up partial melting of this material if you don't have very high power lasers. But if you have using very high power laser, then this is not a problem. In some cases, you don't want to do any melting, because when you do melting and solidification, you have several residual stress related issues. Okay, and you wanted to only do, like, basically you have a powder and then you are applying some glue. Okay, let us assume you are applying glue in a particular way. Only wherever the glue is applied, there the powder particles will be bonded. Other regions, the powder particles are not bonded. So basically you use a binder, and this binder is applied in a specific way how the component is. Like if the component is like a sphere, only the binder is applied as a circle. Okay, so based on, and after you do that, so wherever the binder is there, the material is bonded. The other regions, the powder is free. Okay, so these are whether you melt it fully, partially, or you don't melt it. Okay, so based on that, again you have technologies involved. Okay, so these are different additive manufacturing technologies that we use. So I'm not going too much into it. So I'll try to give you some terminology, like so how the metals are, the components are printed is, although we call it as a layer by layer material addition, it is basically a track by track. You have one track of material deposited, and adjacent to these tracks, you have several tracks deposited next to each other. So when you are depositing one track adjacent to a previously deposited track, there should be an overlap between them. So this is your track one, let us assume. And when you are depositing another track next adjacent to it, there should be some bonding between these two tracks. So there should be an overlap between these two tracks. Then only this region is bonded. Otherwise, there will be some gap always left over. So the distance between two tracks is called as hatch spacing, and it is very important to consider to get defect-free samples. So you deposited tracks next to each other, then you make a layer, and then you deposit layers one over the other, then you have multi-layer, and then you end up having your component. Okay. So there is something called as layer thickness. What should be this layer thickness, hatch spacing, and number of layers, and this is called as tracks. So this is something that you need to understand. And then there is something called as build orientation. I have a cylinder. I can print it in this orientation, in this orientation, in this orientation. Each orientation has its own advantages, disadvantages. So we need to take care of which orientation I am doing. Okay. And then there is something called as fill run and contour run. So based on whether I am making the material. So I told you that in additive manufacturing, predominantly metal additive manufacturing, you have some surface finish issues. To go much better surface finish, you actually use a different process parameter for the contour run and the fill run. So if you have used an additive manufacturing machine, there will be two conditions that you need to give. What should be the fill run parameters? These fill run parameters are predominantly determines the relative density of your sample. Like you wanted a defect-free sample, and that is determined by the fill run, and then you have a contour run, which tells about the defects in your sample. So once I have one layer deposited, how I am making this layer, whether I am making this layer, like this. So you have one track, you started from here, went here, and then again came back to the start position and then went here. So this is called as a unidirectional scanning. So how I am making my layer, okay, or instead of that I go like this, come back, go like this, come back like a snake. Okay, so this is a bidirectional pattern. Okay, or kind of a snake pattern. You started from here and then you entered. So this is your layer. How you are making this layer? Either you are doing like this, or like this, or you are doing like this. You first deposit, you scan these blue regions first. Okay, and then you scan this red region. So then it will become a layer, right? So there is something called as raster patterns. Okay, so how you are scanning your layer. So all these things matter because they determine how the residual stress pattern comes into your sample. So you have chessboard pattern, you have island pattern. So that there are different patterns that you, and there is something called strike pattern. So there are different patterns people use to avoid problems of residual stresses and things like that. Okay, and then there is something called support structures in additive manufacturing. So when you have an overhang, okay, so this is your, let us assume this is your base plate, bottom, and then you are printed this particular part, and then you are trying to print this. If this angle, okay, is greater than 45 degrees, okay, if the angle is greater than 45 degrees, then, so from the surface, so let us assume, then you need something called as support structures. Okay, so because this region is away from the base plate and there is no support for this particular region, so you need to give some support from the bottom, from the base plate, so that it can be also be printed. So there is a overhang angle. So based on the machine, based on the technology that you are using, this overhang regions change. So normally for powder bed fusion technology, laser powder bed fusion technology, till 45-degree angle, you will be able to print without a support structure. But if the angle is greater than 45 degree, then you need some support structures. Okay. Okay. So now I think you have a fairly good idea of the terminology in additive manufacturing. So I told you that if you wanted to make your raw material, first you need to make this raw material either in the form of a powder, wire, or sheet or plate. So the most popular technology is powder-based technologies. Why? Because they give you better dimensional tolerances and things like that. Okay. In other technologies of additive manufacturing, making complex shapes is very tricky. With powder-based technology, making components is reasonably easy. So first you need, let us assume you have in your lab some stainless steel plate. First you need to make this stainless steel plate in the form of a powder. So how you do it? You use a technology called as gas atomization. So basically you melt the plate, and then once the liquid, the material is melted, when the material is actually allowed to flow through a nozzle, these nozzle diameters are generally in the range of 1 mm, 2 mm. and this liquid stream will come, and then you are impinging this liquid stream with some gas, and then you achieve some powders. Okay, I'm not going into it, but what you need to remember is you need a powder in this particular morphology. But when you do this technology, you basically have powders of all these shapes and sizes. So we need to do some sieving. You need to do sieving of this powder only to achieve this particular powders. Okay, and this particular powder morphology will give you good flowability, because in additive manufacturing you need good flowability, and then there are some parameters which are determined or which are given to check the flowability of the powder, something called as Hausner ratio, Carr index, and angle of response. And each technology requires a particular size range of powders. So in powder bed technologies with laser, you have powders required in this particular size range. If it is electron beam, since we can use high power electron beams, so you need powders in the range of 50 to 100, and in direct energy deposition you can use powders in the range of 80 to 150. So you basically require spherical powders in most additive manufacturing technologies. Other than this metal injection molding, sintering and all, it's not additive manufacturing technology, but just for comparison. So once you make your powders, then you do additive manufacturing. Once you have the powders, then you wanted to do additive manufacturing of those powders. So when you do that, you need to first optimize the process parameters. So you have several process parameters like laser power, laser scan speed. As I told you, if you are using laser, then laser power. If you are using electron beam, then electron beam. If you are using an arc, then wire arc, current and voltage, things like that. So based on the heat source that you are using, its power and how fast you are moving this heat source. So this is called as scan speed. Okay, if I am staying at a particular region for a very longer time and then moving very slowly, then I have low scan speed. If I am moving my heat source very fast, then I have higher scan speed. Okay, and then you have hatch spacing, as I told you, the inter-track distance. And then there is something called as layer thickness. What is the layer thickness that you are choosing? And the scan strategy that I told you, that you can scan a layer with different ways. Okay, so either you use a main deer or a snake kind of a pattern, bidirectional pattern, chessboard pattern, and things like that. So you have, these are the main process parameters people play around to arrive at an optimum condition. Okay, so this is a let us assume you have a new material where lot of research is not being published and you don't know the processing conditions. So how to do it? How to arrive at an optimum condition? So what people do is, normally people keep this hatch spacing, layer thickness, laser scan strategy constant. Generally they keep hatch spacing of a particular value. You generally maintain 30% of overlap. So let us assume your bead, your size of your track. Okay, the size of your track is, let us assume, 100 microns. So this is your 100 microns track that you are able to achieve for a given power and scan strategy. Generally, you maintain 30% overlap. Okay, so your overlap distance is generally 30%. So you ensure that you have a 30% overlap. Okay, so this is a general rule for hatch spacing. It's not always correct value, but it is a general recommendation. Okay, and then generally the layer thickness is in the range of 40 to 50 microns. So that is also for most materials people use this. So you know this, so you keep it constant. And laser scan strategy, generally people do a 67-degree rotation with each layer, and they use a bidirectional pattern. So you actually scan like this, you come like this, and then scan like this. So once one layer is developed, then for the second layer, you actually rotate the scan by 67 degrees. So you start like this and then scan like this. So from the first layer and the second layer, there is a rotation of 67 degrees. So this is your 67-degree rotation. So you are maintaining a 67-degree rotation between first layer and second layer. Why this is required is to control the residual stresses and things like that. Okay, I'm not going too much into that, but what you need to understand is generally people keep these recommendations and they keep them constant, and then they play around with this laser power and laser scan speed. In the case of laser, it is laser power. In the case of whatever is the heat source, it's power and it's scan speed. Okay, so you develop different process parameters. Let us assume you keep laser power of 40 tungsten volt and watts, and then 200 speed. So you do one experiment, and once you do an experiment, you cut the sample and check whether my sample is having any defects or not. If it is having defects, then you mark this point as it is having defects. If it doesn't have any defects, so then you mark the point as there are no any defects for this process parameter. So all the regions wherever there are defects, you mark them as defective regions. Regions which doesn't have defects, you mark them as no defect regions or fully dense sample. So then you get these processing maps. So you are basically telling in this particular region, you don't form defects. Okay, in this region, because you are at a very low power and very high scan speed, you are not able to melt. You are not the heat source is not very hot, or the melt is not happening. So that's why incomplete melting. In this case, because you are having very high power and very low scan speed, you are overheating. The same region you are staying for a very long time because your scan speed is very low. Then you end up having overheating. In the same case here also, till a particular scan speed, you have overheating problems. After a particular scan speed, when the scan speed is very high, reasonably high, then high powers will also result in good density. So this is about processing maps. So my work predominantly we are actually working in how to optimize these parameters without doing experiments is what we are trying to do, because additive manufacturing, as you know, these powders are very expensive and the availability of this machine and things like that are also very difficult. So how to arrive at these optimum conditions is something that we are looking. So what are we optimizing? We are trying to get rid of these defects like gas porosity, lack of fusion, unfused powders, balling, delamination, warping, cracking, and things like that. So now we saw that there are several types of defects, and these defects, some of the defects can be controlled by process parameter optimization. But there are some defects which are material related. They are not process related. So some materials, irrespective of whatever process parameters you use, you always have defects. So this is one of the major problem in additive manufacturing. Why it is a major problem in additive manufacturing is because you are not melting the whole material at the same time, right? In additive manufacturing, what we are doing, we are actually melting a small region, and then you are again melting a small region. Again, you are melting a small region. So there is a localized melting in the case of additive manufacturing. But in case of casting, what you are doing, let us assume this is the shape of the component that you want. You melt the whole material at one time and pour it. So in casting, the way the material is experiencing the thermal cycle in casting, the way the material is experiencing thermal cycles in the case of additive manufacturing is significantly different. In the case of additive manufacturing, the material is not experiencing heat at the same time. The material is experiencing heating, cooling, reheating. When you are depositing this particular layer track, you are reheating this particular track. So there are multiple remelting, and when you are melting this region is remelted again. So you have several remelting, several reheating, several the material is also localizedly melted and solidified. Okay, so because of that, you have several issues like cracking. If some materials are very difficult to process, and those will be very difficult to do additive manufacturing. So one general recommendation when you do this additive manufacturing is you choose materials which are easy to weld. If a material is easy to weld, then most likely it is easy to additive manufacture. So if your selection if your material selection is in this particular direction, then in this case, something like this. So these materials which are indicated here, they are easy to weld. So if I take any of this material like IN718, and if I do additive manufacturing of this particular material, I can easily optimize the process parameters and get defect-free samples. Okay, but if I take in this particular region, okay, it is slightly difficult to weld. So during additive manufacturing, also optimizing process parameters will be difficult, but I might get some defect-free samples. But these materials which are indicated here, like very difficult to weld. If I wanted to do additive manufacturing of this material, it will be very difficult. You will always have some cracking. Okay, so if you see, so these recommendations have to be followed. So when you do process parameter optimization, you should remember it is not only the process parameters which will determine, it is also the material selection also is important. So if I select a very difficult to process material, additive manufacturing will create more problems. If I take a material which is easily processable like weldable, then my additive manufacturing process parameter optimization is also reasonably easy. Okay, so now we saw that how to make the raw material. Once you make the raw material, we saw how to optimize the process parameters. Once you optimize the parameters, I told you that your material selection is also important when you are optimizing the parameters. Once you fabricate the part, so these are some recommendations to achieve defect-free parts. Like you wanted to, you maintain this L by D ratio, W by D ratio. These are some ratios given. These are general recommendations. It may not be true for all the materials, but it will be true for most of the materials. Okay. So once you make the part, then there is something called as microstructure. So I'm not going into this now, considering the time that we have. So I will skip this part. So what I am trying to give you an idea is, since additive manufacturing, I told you that the material is deposited track by track, layer by layer, involving several remelting, reheating cycles. Fabricating the sample, or when you see the microstructure of the material which is fabricated by other routes and the microstructure of the material which is fabricated by additive manufacturing route, you have a significant difference. So because of this significant difference, you have significantly different mechanical properties, or it is important for people to study the mechanical properties. I have material A, let us assume stainless steel. I have made this material through casting, machining, and things like that. Same material I have produced the component through additive manufacturing. If I check their microstructures, they will be significantly different. And so it is important for somebody to check whether their mechanical properties will be same or not. Composition is same, only thing is the way I processed this component is different. So whether I'll get same properties or not is something that somebody has to evaluate, and that a lot of research is going in that particular direction. Okay. Okay, so I'm not involved too much into that particular aspect, but I'll give you some ideas of where additive manufacturing is currently extensively used. So one thing that you need to remember is, I think most of you would have realized that additive manufacturing processes are very expensive, or the technology is very expensive. So if I wanted to make a simple hinge like this, you should not use additive manufacturing, because it is not a cost-effective process for making a simple design. Additive manufacturing will be costlier than your traditional machining or casting kind of a technology. But if I make this design of hinge into something like this, where I try to do some topology optimization, where I am trying to reduce the weight of the component. Okay, I'm removing material wherever it is not required. I'm keeping material wherever it is required by doing some topology optimization. So if I change this hinge design to this, okay, where it is little complex than this, then additive manufacturing becomes cheaper than your traditional manufacturing. If I wanted to manufacture this through machining, okay, I might spend more money than additive manufacturing. If I make this design more complex, like I make this particular beam or into a hollow beam with a lot of internal structure, then with conventional manufacturing, this cannot be manufactured at all. Then additive manufacturing is the only way. Okay, so additive manufacturing is viable solution only when your design is complex. When your design is not very complex, when your design is a very simple shape, then additive manufacturing is a viable solution. So you need to look for simple manufacturing. So based on the process that you are using, okay, based on the component and its design, whether additive manufacturing is a viable solution or not is something people should understand. And there are several applications industries are looking at. So if you see this by 2028, I have given you a comparison of automotive sector here, which where you do a lot of mass production. So people show that there is a huge trend in increasing the final components in automotive. So I'll give you some examples. So people see of making this cycle rim completely through additive manufacturing for bikers who were specifically designed for a particular person. Okay, people also look at manufacturing some of these nodes for a carbon fiber bike. Okay, and people look at these rims for high speed bikes because speed is an important criteria there, weight reduction is an important criteria there. And then people also talk about this exhaust, fabricating of this exhaust walls, where basically you are at a very high speed. Let us assume your car is at a high speed car going at 200 kilometers per hour or something like that. Then you need to also exhaust the gases coming from this engine at the same speed. So your exhaust system becomes very, very important. So additive manufactured exhaust systems are currently used. And people also look at reducing the number of assembly parts. So in your, so this is your seat belt assembly. So where you engage your seat belt, no? So this is what we see, but it is actually made up of 8 different components and they're assembled into one. So all this assembly time, making with different suppliers, bringing them, integrating them, assembling them into this, you can make it in one shot and you can also reduce the weight. So there is a lot of interest in that. So people show 40% lighter. So lot of interest in EV sector where you wanted weight reduction of the car for better mileage. Okay, and these fuel injection nozzles become extensively used. I think GE is using these fuel injection nozzles in their rocket gas turbine engine. So it's basically made up of multiple components, and you make all these components in one shot through additive manufacturing. And there is a lot of prototyping. Most of these Indian companies, Maruti, Mahindra, all these people are extensively involved in this prototyping. And then if you wanted spare parts, let us assume there are classic cars of 1920, 1930 cars, where you will get the spare parts now. So additive manufacturing again becomes an important tool. So that is what I showed you, that peak of lot of investment is automotive is in these particular regions, and there is a lot of customization. You come up with your own design, people change it through additive manufacturing and give you, and there is a lot of interest in tooling also. People develop these titanium based tools. If you are doing some ram type boring machine, this is basically a boring machine. So this is your boring head or your machine head, and you are almost a meter away from the milling head. So there will be a lot of overhang and cantilever effects, and there will be a lot of charring and sound. So people come up with these high strength titanium alloys, weight reduced alloys with these designs. And Sandvik is into this, and there is showing a 200% productivity improvement, conformal cooling channels, acoustics. A lot of interest into this acoustics domain also, where you can develop physical instruments through additive manufacturing, because you can play around with their shape, design, architecture. You can control the sound waves by changing the design and things like that. Okay, so these are some applications. So I'll give you an idea what we are doing in AI/ML. Now you know fairly good idea about additive manufacturing, and there are a lot of applications in additive manufacturing. So I think if you would have come across for AI/ML, the major problem for you in AI/ML is data. So let us assume I have an X material. I wanted to optimize the process parameters of that X material. So if I wanted to optimize the process parameter, first I need data, like somebody has done with X parameters, they found defect. Y parameters, they found defect. Z parameters, they did not find defect. or some other parameter, they found less defects, things like that. So you need large data set of parameter and defect mapping. So some data should be available for this parameter defect mapping. When you have this data available with you, then you can use different models and then try to get this information. So what we did is we also did the same way. So we have taken for TI64 material. So we could collect some close to 180 literature data. Okay, so we have collected data with respect to laser power, scan speed, and hatch spacing. So what we did is any material or any report which says you have relative density 99.5, we consider that material as defect free without any defects. Any relative density less than 99.5, we thought it will have defects. So this is your data. So with the defects and without defects. So we found a correlation between scan speed, laser power, hatch spacing, laser power, hatch spacing, scan speed. So these are your pairwise plots which will give you relationship between both. And we see that there is a fairly good relationship between the scan speed and laser power. So whenever you have these relationships are important. Then we applied different ML models like support vector machine, buoyancy optimization based model, ensembling methods. Okay, and we also looked at the synthetic minority oversampling techniques. Okay, but most of these methods did not give us good predictions. Only ensembling methods and then booster and random forest methods actually provided us the best result. Then if you see this is our test data and this is our predicted data, and we are having close to 80% accuracy. So basically what we are trying to say is if zero is the sample without any defects, okay, 25 times uh, uh, my algorithm is predicting correctly and 5 times it is not predicting correctly. In the same way, when one is a no defect or defect region, 6 times it is predicting correctly, 4 times it is not predicting correctly. So this is the problem. So this problem can be, or we can solve this problem only if you have large data set. When my data set is very large, I can improve this algorithm further so that my accuracy improves further. Okay, but from where I'll get this data set? If I wanted to do experiments also to generate this data, I might be able to generate 30 points, 40 points, 50 points, not more than that, because it's a huge resource and money involved. So what we thought of doing is we thought of using some simulation tools. Okay, so there are we started developing some thermodynamic simulations, a software called ThermoCalc. So we try to simulate the additive manufacturing process that we are doing. So once we simulate the process that we are doing, we have used two different processes. One is ThermoCalc and another one is AM Prava. So these two technologies we use, and then we kind of do single track experiments. So basically we are trying to measure the bead width and depth. So, and we are checking whether the softwares also predict my bead width and depth with respect to experiments. So these are your experimental data and these are your software information. So we are actually getting close to 20% error with respect to width in both the softwares. But in the case of depth, we are having a very high error, close to 60% error in both these software. So currently we are optimizing this software so that we come very close to the reality or the experimental data. Once we do this calibration, that my software is predicting very close to my experimental data, then the software can actually generate these processing maps. So I can use this software to generate the processing map. So with different laser power and laser scan speed, once I know my software is predicting very close to the experimental data, then I can believe these processing maps. So once you have this processing map, you can get large data set from this processing map, from the software data. And this can be used for ML. So we are actually doing these experiments, and then we are using this data for my machine learning algorithm optimization. Once I optimize this my ML algorithm, so I can predict the exact optimum conditions for my material. Okay, and this will be again, it is important to remember this is specific to a particular material. If you change the material, then again this procedure has to be followed for that particular material also. Okay, so these are some simulations that we have done in showing you how we get these additive manufacturing simulations to get this data. Okay, so this is one aspect where we are working. Then I told you that there is always a need of developing high strength materials. Okay, so I told you that there is a infinity possibilities of combinations that you can get these high strength materials. So what we have done is we collected large data set, okay, of whatever is available. So what this ultra high strength steels is greater than 1500 megapascal. When the yield strength of your material is greater than 1500 megapascal, then then you call them as ultra high strength material. So we collect data of close to 170 plus material combinations, and then you do this model training, and then we do different algorithms again: linear regression, support vector regression, k neighbor regression, random forest regression, and xg booster. So we have several data set. Okay, so when we collected data more than 1900 megapascal yield strength. So we have taken close to 180 data sets. So here the whole idea is you need composition. So which composition of my material will give me yield strength greater than 1900 is what we wanted. So so the model is developed to predict which composition will give us this. So you can we have collected all this data, and then we saw that there are some elements which are mandatory or which are definitely required to achieve that. So we do this mapping of different elements, and then their requirements. So then our observations are like we were able to develop this model, and then with the model we were able to get some composition. So to validate whether my machine learning model, whatever composition that I have achieved, whether I really get this experimental data, we actually developed this composition targeting this yield strength greater than 1900 megapascal and elongation 10%. This is our target, but we will see how we are able to achieve. So we melted this material, we developed this material, we did some microstructural analysis, and then we have hardness values here. So you can see, since the material that we developed is very small, we could do only hardness survey here. So the melted material is having hardness close to 600 megapascal, 600 HV, sorry, 600 Vickers hardness. So there is a simple thumb rule that yield strength is generally 3 times its hardness. So if you see, we are coming close to 1900 megapascal of strength that we want. It's an ongoing, all these works that I showed you, they're all ongoing, but I just giving you some ideas where we can use machine learning and then validate the data, whether we get these parameters or not. So this is all about my content. So I'll stop here, and if you have any questions, maybe you can ask. Hello?
Yes, sir. Hello. Yes, sir.
Yeah, if anybody has questions, maybe I can answer.
Yeah. Dear participant, if you have any question, please. Hello. You can ask question to this. Any participant, if they have any queries, any questions. Good. Okay, sir. So, dear participant, now we'll go for the vote of thanks for today's section. If you have any question, any regarding, so you can just text us so that we can convey the message to sir. If anybody wants to ask, now the platform is open. You can text, you can put the question in the chat box.
Okay, if there are no questions, then
Yes,
I'll
sir.
stop here.
Yes.
Yeah, thank you.
Just a
Thank you
minute,
very
sir.
much.
Yes. Let's move for the vote of thanks. A very good afternoon to everyone on behalf of the Department of Mechanical Engineering, Lords of Engineering and Technology. It is my privilege to extend the vote of thanks for the second section of so on behalf of the Department of Mechanical Engineering, Lords of Engineering and Technology, it is my privilege to extend the vote of thanks for second section of the day in our 6-day virtual national level faculty development program. We are truly honored to have with us today Dr. Manogana Karthik Gangaraju sir, Assistant Professor, Department of Mechanical Engineering, IIT Bhubaneswar. Sir, your highly insightful and academically rich session has given us a deeper understanding of the advanced development in metallurgy and material engineering. Your extensive academic journey, beginning with your BTech in production engineering, followed by MTech in welding engineering from IIT Tirunachipalli, and you are communicating to excellent in research. We sincerely appreciate your valuable time, clarity in presentation, and the depth knowledge you shared with our participants. On behalf of mechanical engineering, I thanks to the sir and our heartfelt thanks to the management, principal, and head of the Department of Mechanical Engineering to continue encouragement and support in organizing FDP. We also we also express our gratitude to the organizing committee and technical support team for their dedicated support in this FDP. Once again, thank you all for making this section a grand success. And now I request all the participants to please give the feedback of today's session. It is feedback link is already shared in the chat box. Thank you, and all.
Thank you. So I'll leave now. Huh? Okay, thank you.
Thank you, sir. You may leave.
Yeah, thank you.
Yes, dear participant, we have today one more session from Professor of Osmania University, Dr. Goda Hadia sir. Sir will join over. Yes, we'll resume the session within a 5 to 10 minutes. So all participants, please be there in the meet. Soon we're going to join the second session of today's second day. Thank you.
Next.
ఇప్పుడు ఓకే సార్, మీరు మైక్ మ్యూట్ చేశారు సార్.
Good afternoon, everybody. Welcome back to our faculty development program. Let's get refocused and dive into our next session. Today we are having our guest, Dr. Boda Hadya sir. Dr. Boda Hadya sir is working as a professor and chairperson of BOS Autonomous of Mechanical Engineering at Usmania University, Hyderabad. Sir has completed his engineering in mechanical field from Usmania University in 1999, MTech in thermal engineering from JNTUH in 2005, and PhD in refrigeration and air conditioning with a specialization in HVAC from Usmania University in 2016. Dr. Hadya sir has an extensive teaching career, starting as a lecturer in mechanical engineering with the Department of Technical Education, Government of Telangana, India. He then joined Usmania University, where he progressed from an assistant professor to an associate professor and ultimately to his current position as a professor. Workshop and courses. If you talk about the workshop and courses, Dr. Hadya sir has participated in various workshops, orientation programs, and refresher courses related to thermal engineering, heat transfer, and related fields. These programs were organized by reputed institutions like IIT Roorkee, IIT Bombay, UGC, and others. Sir has an area of research in thermal engineering, turbo machinery, refrigeration and air conditioning, HVAC, and heat transfer. Dr. Hadya sir has delivered guest lectures on topics: the performance evaluation of air conditioners using different refrigerants and software tools, recent trends in air conditioning system with different refrigerants, a comparative study of air conditioning system in conventional vehicle and future electrical vehicles. Dr. Hadya sir has received awards for presenting the best paper at the ICMAE 2012 conference and is actively involved in various academic research activities. He has published research papers in various national and international journals covering subjects like refrigerants, thermodynamic properties, performance analysis of HVAC systems, and more. We welcome you, Dr. Hadya sir, for our 6-day national level virtual faculty development program. The session is all yours.
Yes, sir, please unmute yourself.
So we request Hadya sir to please unmute yourself.
Okay, can I hear you now?
Yes, sir. Right. Open the PPT, sir. Open the PPT, sir.
Okay.
Yeah, you are visible. Open the PPT, sir. Sir, enlarge. You can start, sir.
Yeah, can you see
Thank
the
you.
PPT?
Yes, sir. Yes, sir. You can carry on.
Okay.
Thanks.
Good evening, all the participants of this 6-day FDP program and all the faculty of Lord's College. And first of all, thank you very much for choosing me as the expert in this particular area, research methodology and experimental research design. So thank you very much, Professor Suman, the head of the department, and all the principal. Okay. So, and also the participant. So today topic is research methodology and experimental research design. So I have divided this particular talk in three segments. We'll be talking the basic requirements of the experimental research design and significance of the research methodology and various aspects related to the research methodology. And second one is the as part of the research methodology. So the how the research report organization should be taken place, and one case study. So coming to the first one, introduction to research methodology, the first part of my presentation. So first, the overview of this my presentation is origin of the research, word research, types of research, research methods versus methodology, research process, criteria of good research, major limitations in conducting a research, necessity of defining the problem, techniques involved in defining a problem, problems encountered by the researcher in India, and experimental design. So the first one, the origin of the word research. As the slide shows, the actually there is no special meaning. The name itself, research. That means already whatever we want, it is exist in the nature. Only thing is we have to find and then find and the search for that solution. So that is nothing but the problem identification for better utilization of the society in general. So if you can see here, it is a careful investigation or inquiry of specially through search for a new facts in any branch of knowledge. Okay, any branch, if you go for, especially in mechanical engineering, we have thermal design and the production. Then especially if you go for again research related to the refrigeration and air conditioning, suppose knowledge of psychrometry also you should have the knowledge. So in that, what is that, what are the various environmental issues and how to the relative humidity and other psychrometric problem. So to design the air conditioning system, already we know the air conditioning system is a simultaneous control of temperature, humidity, cleanliness of air, and then the purity of air. So in those parameter, so based on the region, based on the space, and based on the, I mean to central area of India, suppose coastal area, based on that we have to find the solution for particular region so that we can optimize comfort condition. I am talking about that particular example of related to refrigeration and air conditioning. Then okay, what is that motivation in research? So what ultimately as a student or a scholar or a general industry will get benefited from this research? First one is to desire to get a research degree along with the substantial benefit. Second one, the desire to face the challenge in the solving and unsolved problems. Desire to get intellectual joy of doing some creative work, and desire to get respectability and service to society. Develop your new products and save the cost. These are the motivation for the good research. Then if you can see here the types of research here. So starting from the basic research to the on the basis of methodology, it has been divided: pure research, applied research, and then exploratory research, descriptive research, and theoretical, empirical, and qualitative research. It has been classified into 4 types. Then if you come first, the fundamental and applied research. So fundamental research only to get or gathering the knowledge for a knowledge sake only. So only to understand the phenomena are related to the pure mathematical or example of the fundamental research. And if you can see that applied or action plan related research aims to find a solution for the immediate problem facing a society or industrial. So suppose the industry which is facing any problems, that problem should be find out by applying that particular approach that comes under the applied research. And other also you can see that descriptive analytical research. So four categories: quantitative and qualitative research. Quantitative research is concerned with the quality phenomena, and the quantitative research is concerned with the based on the measurement of the quantity or amount. So again, it has been categorized into three, that is the inferential, experimental, and simulation approach. Regarding these experimental and simulation approaches, in subsequent slide we are going to discuss particular one. Then these are the comparison of various quantitative and qualitative research. And then significance of research. Okay, what ultimately this research signifies. One is the research provides the basis for nearly all government policies in our economic system. Suppose government of Telangana, suppose if the government is wish to take any monetary benefit or the family related benefit to the, then they will consider the each demographical number, and so that the number of male and female and the based on the age also they will consider categorize, so that will indirectly benefit to the society. That's what the first one, the first research significance is provide the basis for nearly all government policies to be implement any policy. So the data should be there. So data collection and then optimization of data is plays very important role. And coming to second point, research has special significance in solving the various operational and planning problems. So mostly this related to the to solve the problem which are relevant to the industrial and whole. Then research is equally important for social scientists in studying the social relationship and seeking the answers to the various social problems. Then the research methods and research methodology. So far we have discussed the what is research and what are the various types of research. And next is coming to the next slide is the research method. Research methods are the tools and techniques. So what sort of tool or simulation tool if that used for that particular research, and then what sort of techniques are being used to generate data, gather data, that type of that is called as a research methods. And methodology is different. So what is that methodology? It is the systematic plan and procedure to solve the problem, step by step procedural steps to adapt and come to the conclusion. That is the research methodology. So what is that method? Method is nothing but the tools and techniques used, and methodology is the plan and procedure to be adopted to find the solution for a particular problem. Then come to the under this particular research method, researcher use in performing research operations into following three groups. One is in the first group, which are concerned with the data collection, and then the statistical techniques to be used and evolve accuracy of the result obtained. Then next is the research method used for the conduct of the research. So the various sources of the sources are there. You can go for the library research and the research field, non-participant direct observations, participant observation, mass observation, and mail questionnaires, group interviews, and telephone survey you can conduct. Then research methodology. Just now we have discussed it is the systematic technique, systematic plan, and then procedure used to identify and analyze the information regarding the specific research topic. So why research methodology is important? Because a research methodology provides the framework and guidelines for researchers to clarify and define research questions, hypotheses, and objectives. Suppose you want to, after getting the gaps in the literature review, then the third chapter will come, the research methodology, where you have to define the problem statement and then the objectives. So what would be the objective generally? To analyze, to investigate, to compare. Like that statement, you have to state your objectives. So that really gives the framework and guidelines for the researchers. Second one is it helps to researchers identify most appropriate research design, sampling technique, and data collection and analysis method. So then research process. If you can see here, step 1 to 7. The first one is the define research problem. Second, review concept and theories. Review previous research findings. That is the step 2. Then after a review step, you have to formulate the hypothesis. And then the fourth stage is the design research, that include the sampling design and collection of data, and then analysis of that particular data which you have collected, and then interpret or prepare a report. So then you have the feedback and feed forward as well. Based on that analysis, again you can reconsider the parameter which are influencing in a particular approach. Then you can reconsider that particular variable, and then you can obtain your for the validation. Then the criteria of good research. So the purpose of the research should be precisely defined. The research procedure used should be described in sufficient detail, keeping the continuity of the further studies. So that's what in a journal paper, what generally we do. So the a research scholar or the any author who publish the paper, first we'll see that abstract of that paper, and then after that what sort of methodology he has adopted, and then the ultimately we finally go to the conclusions. So what conclusions he has made, based on that that would become the feature scope for our problem. So that's what understanding the abstract and following the methodology, and the understanding the conclusion, what the previous researcher has done, that is more important. And coming to the third point, the procedural design of the research should be carefully planned to yield the results. And the research should report the complete frankness, flaws in the procedural design, estimate their effects upon the findings. The analysis of data should be sufficiently adequate to reveal its significance. The validity and reliability of the data should be checked carefully. Conclusions should be confined and to be summarized based on the objectives. So in general, three words I can say you can finish your research task, that is GOC. So first, G means the gap identification. So gap identification generally we find through the literature survey. So at the end of the literature survey, we can come to the conclusion that what are the gaps, or which experimentation previous studies have been carried out, or what parameters the previous researcher has done. So based on that, so gaps identification is the more important. So then those gaps will be converted into fixing of the objectives, that is GO. O is for the objectives, and then so you have to at least to formulate, or you have to mention the 3 to 4 important gaps, and then fifth would be the validation of your work. Why? Because you at the end you have to compare your work with other researchers which they have carried out, where it is experimental or simulated. So based on that, validation is much more important priority to be given for the any researchers. And coming to the last one is the drawing the conclusions. So then the major limitations in conducting research, that is the time, cost, and access to resources. So the many research face difficulties is that the resource availability of resource is a bigger problem. Then the approval by the authorities, ethical concern also very important parameter, and then expertise. And then necessity of defining the problem. Just now we have discussed what, so at the end of the literature review, very beginning of the research methodology chapter, you have to formulate your problem. That is problem formulation, also called as a problem statement. So you have to define, just like what is there in the library, in the labs generally we conduct. Suppose if you go for the third semester or fourth semester, the IC engines are there. What is that problem formulation for that? That is nothing but the aim. How do you define the aim of that a particular experiment? The aim of this study, or the aim of this compression ignition engine, is to investigate the performance parameters of that engine. Then what would be the performance parameter? You talk about the efficiency of the engine, mechanical efficiency, isothermal efficiency, adiabatic efficiency. Okay, thermal efficiency plays very important. Then at a mass of fuel consumption. So like that, you have to define the problem or problem formulation. The manner in which the problem is defined decides the direction of the entire research. The problem that has to be analyzed should be defined clearly. A careful scrutiny of the research problem will help in working out the research design. So that's what the defining the problem plays very important role in the methodology section. Then lot of questions may arise during the course of the research. Then what sort of data to be collected, what characteristics of the data are relevant and need to be studied, and then what relations have to be explored, what techniques have to be used for this purpose. So data collection plays very important role for us. It is not the big task like social sciences research, especially if you come to the mechanical engineering. Then how do you collect the data for a refrigeration and air conditioning? So if you think about that comfort conditions, so you have to talk about the number of persons sitting in the hall. Based on that, the heat generated by the each person, then what is the air velocity of that particular one, and then the what is the tonnage of the particular room to be required. So based on that, the operating temperature and pressure required and relative humidity. Already we have discussed what is that refrigeration. It is a simultaneous control of 4 parameters: temperature, humidity, cleanliness of air, and then the purity of air, velocity of air, 4 parameters like that. So data is needed. Until and unless you don't have any data, we cannot predict the required temperature. So if you then first let me know, what do you mean by that comfort in general in air conditioning system? What do you mean by comfort? Anybody, what do you mean by comfort? I think all of them are participants are mechanical engineering only. Hello, can you hear me, anyone?
Yes, sir. But most of them are mechanical, sir. Some are from other department.
It's okay. Then now I'll define what is comfort air conditioning. It is nothing but the state of mind which expresses the satisfaction towards the thermal environment. For designing for air conditioning system, the state of mind which expresses the satisfaction towards the thermal environment. The name itself, the thermal environment, which gives the 4 parameter itself. 4 parameters: temperature, humidity, cleanliness of air, and then the flow of air. So like that, so here the lot of questions may be arise during the course of the research. That means the what sort of data to be required to analyze the problem, what characteristics of the data are relevant and needed to be studied, what relations have to be explored. So there is a relation between, suppose if you go for the what is that the sensible heating and sensible cooling. So you cannot do at a time all the sensible heating, cooling, and humidification, dehumidification. So then step by step procedure to be adopted to get the comfort condition. So this type of data to be required for analysis. So these are the techniques involved in the defining the problem. So these are the statement of the problem in general way, understanding the nature of the problem. So what is the nature of the problem we must understand first, and then next surveying the available literature. So the chapter 2 what we have discussed is the deciding chapter, where a researcher can get or identify the gaps from that one. That's what surveying the available literature is, plays very crucial role for researchers. Developing the ideas through the discussions. So while interacting, just now we have I have posed a question. So what was the question? What do you mean by comfort condition? Like that, the interact you will immediately think. So sir is asking the comfort. What is comfort? Comfort in terms of the environment, comfort in terms of the money, comfort in terms of the family, all the important parameter. But your research is in the design of air conditioning system. Then your focus would be on designing the parameters of air conditioning system. That's it. And other relevant techniques also here. Fifth one, the research, the family and then the researcher must sit and then discuss the parameter which are involved. Then the experimental design. Now, as per the title which I have given, the experimental design which I am showing, discussing, I'm going to discuss in a subsequent second and third sections. We'll discuss here. The design is nothing but the tools and techniques to be required to solve the problems. What sort of the tool and what sort of the technique to research is going to adapt. So that we are going to discuss here. So then if you can come here, the overall design, this is the flow chart for the research design, operational design, sample design, observational design, and statistical design. And then features of the good research, here you can see the flexibility and economical efficient, and then so minimization of the bias, okay, maximization of the reliability of the data which you are collecting, that should have the realistic one, and a design which gives the smallest experimental error. It should not involve the error should be less than or plus or minus 0.001. Then studies related to objective and nature of the research problems, all above must consider with while preparation of the research design. So then the types of research design, you have exploratory, descriptive, and then hypothesis type of there. So then the next, what are the characteristics of the research design also is there. You just understand the basic characteristics, and then problems encountered in research in India. So first one is the lack of scientific training. So most of the research, they don't know the methodology, how to carry out, or the scientific training is lacking behind. And second one is the insufficient interactions. So most of the research always feel that, okay, I don't know what to do. Then they themselves, they'll so bother a lot because the lack of interaction with the other researchers or the higher professors or any required source, they are unable to interact with them. Then need for the generating the confidence, and then overlapping, and then library management also very poor in India. So those are the problems encountered by the researchers in India. So then the first part is just now we have discussed. So if you quickly review that particular topic, what we have discussed in the first one is the basic introduction of the research methodology, types of research methodology, and then significance of research methodology, difference between research methods and research methodology, and other problems, and then the formulation of the problem. So topics we have covered. And then next come to the structure of the thesis. Suppose you have well aware of that all the collection of data, analysis of data, and then you want to write a thesis, then how it should be. So first one is the title paper. So the title of the slide. Second one is the abstract. So what exactly you mean the abstract? So abstract is the mini statement of entire thesis. Suppose the thesis has the 220 pages. So the very beginning, or any expert who is going to review, he need not study all each and every paper. The first paper itself, he can understand that what is there in that thesis, so that he can come one basic prior conclusion. So then what is that significance of the abstract? Abstract gives the mini statement of entire work. It should be in the form of 3 para, which defines, it should be in the form of 3 para. Those 3 paras are IMR format. I is the basic introduction, I for introduction. Second, so you talk about the introduction about your work, and then the process involved, parameters, and then basic model. So that is the I. Second one is the method. So IMR. Second para should be the M. M is the method. So during research methodology, what sort of method you have adopted, whether it is experimental or simulated or the analytical, as the your FDP program title gives the analytical approach like that. So what method is there, you need to mention in the second para. And then the third one is the sample result. Not all the result should not be reflected in the abstract. Highlighted results you can show in the abstract. So that is covering the entire abstract in a 3 para. That is enough. Basic introduction and methodology and the highlighted results which you got. Anyhow, you will be explaining in the conclusion chapter results and also the results and discussion chapter, but the important results which are contributing the in the process parameters that you need to incorporate in the abstract. I hope you got it. So 3 para wise, that is IMR format, you can discuss. And then coming to the next introduction. So introduction point, so where you can discuss the basic introduction. It should not exceed 8 to 12 pages. You can see here abstract is a 3 para. I have given some abstract model over here. You can see the sample model of this abstract. And then introduction is the basic parameter, and then the defining the various application advantages, and then the any form of, suppose if you go for turbine, so regarding turbine, various elements which are involved in the turbine also you can discuss. And second chapter is the literature review, so which review what has been done, and then the critique the literature and identify the gap and a problem needed for this literature. So gaps identification provides very important. Then writing the literature review, so you should not write all the author's name in the literature review. Only if it is a first author, the first author name followed by year or number, whatever you feel comfortable, you go better for with the number. And second one is the suppose if you see here second number, that is Alireza Riai et al. What do you mean by et al? And also some more also is there, that so more than 2 authors you need to mention et al. If it is a single author, only first name and then the number, that's it. So more than 2 authors, so you need to mention the et al. So like that you have to nomenclature the literature review section or chapter over here. Then gaps identification. So already we have discussed identifying the gaps plays very important role. That gives the futuristic understanding, and then what sort of problem you need to carry out the identification. At least 3 gaps you have to mention. Then how it should be. So many researchers focus on the simulation model. There is a lacking behind the experimentation. So many, because of the to conduct the experimentation, the lot of cost involved, time involved, all those things will be there. Then the many research what they do, generally they go for the simulation approach. So then we cannot always depend on the simulation approach. It is better to conduct the experimental. So then you need to, suppose if you wish to conduct the experimentation, then you highlight that many of the research focused on the simulation. Since they have done simulation with same parameter, I am going to investigate experimentally. Like that you have to mention. Then second one, the very less literature is available in the selected materials and methods. Very important. The very less literature is available on the selection material. The previous researcher, of course, he has considered some of the materials. That material may not suit for a particular application. Then you can reconsider, and then you can mention this very less literature is available on the selected materials and methods. What method he has followed also you can mention over here. And there is need to research methods and then methodology. Okay, what methodology they have followed, you can highlight this particular section in the chapter 2, especially the gaps identification. So then the methodology, as we have discussed, chapter 3 methodology, the problem statement. Very first, the problem statement should be, it is a concise and then accurate explanation of the problem that a study aims to address, it points out the gaps between the desired and actual state and emphasizes the necessity of conducting research to bridge this gap. So that you have to define. Simple way, it should not exceed more than 3 lines. So problem formulation or problem statement should not exceed more than 3 lines. Suppose my research in refrigeration air conditioning to evaluate the performance of the air conditioning system. Then how should I the formulate, or the how should I the problem statement I should make? The aim of this research is the experimental investigation of the vapor compression refrigeration system to enhance the system performance. That's it. Okay, like that you can mention or you can formulate your problem. Okay, I have formulated problem, that is the system performance improvement. Then to be improved the system performance, what should be the objective? To first I have to fabricate the vapor compression refrigeration system for a split air conditioning system. That means the indoor conditions and outdoor condition I need to take care. And next one is the to analyze the refrigerant properties. So considering the thermodynamic and transport properties of the refrigerant. So like that. So in case study we will discuss particular objectives. So then the research flow chart. So this flow chart gives the what the researcher is going to do in a sequential steps. So this starting from the what we have discussed, abstract, introduction, literature review. Then I have carried out the simulation study, and then the experimentation also is there. Both should be compared. That is nothing but the validation. So if the validation between the simulation and experimental is within the 5 to 10%, that is acceptable, so that I can go for the conclusion, or else I need to reconsider. So that's what the feedback is also given either for experimentation and simulation, and I need to re-exercise that particular parameter. Suppose I have given the mass flow rate is very high. So to mass flow rate very high means again the compressor work is more, and then the COP will be reduced. So what I need to do? I need to have a regulation onto this flow of mass flow rate, so that the work of compression can be reduced. So like that, reconsidering our feedback system should be given, so that the system experimentation will be carried out. So with less accuracy, the validation should be experimental and simulation should be within the range of 5 to 10% is acceptable. So this is the experimental procedure. Next in case study we will discuss results and discussion chapter, 4th chapter actually, and 5th chapter is the conclusion and scope for future work. So in after results and discussion chapter over, then you immediately move to the conclusion chapter, where you can mention the highlighted results. So based on the objectives, suppose you have fixed objectives, four objective you have mentioned in the methodology chapter, then how many conclusions you should draw? At least 6 to 8 conclusions should be there. So each objective should be concluded with 2 conclusions. So suppose if you have given 10 objectives in the methodology chapter, then how many conclusions should be there? 10. Okay, so double the objective is the more better always. Okay, then at the end of the highlighted conclusions, you have to definitely mention the scope of the future work. Scope of the future work should be written. At least suppose you have worked out on a particular refrigerant, so that will be compared with the other refrigerant. Then what you need to mention? So since the work has been limited only R32 refrigerant, so any other refrigerant with low global warming and low potential global warming, ozone depletion potential refrigerant may be used. Like that you have to use. And then this research has been carried out only simulation. The work may be further carried out for experimentation as well. Like that you have to mention the future scope of work. Next, the references, very important references you need to mention. If you have pen or notebook, you just write down always reference should be number 1, square bracket 1, followed by A for the author, A, then followed by Y for year, author, followed by year, then T, title of the paper, AYT, title of the paper, then followed by J, journal name, J for journal name, and then VIP, volume, issue, page number, volume, issue, page number. So like that, in that pro forma you can write here. If you see here, first one square bracket is there. You can see here square bracket, then followed by the some author name, Chanarong Wantha, author A, followed by year. Okay, then the inverted commas, you can see the experimental investigation of the influence of the thermoelectric subcooler, and some title is there. That is author, year, now the title of the paper. Then in which journal this paper is reflected, that is the applied thermal engineering. The journal AYTJ, J is the journal name. Volume you can see 180, issue 115829, and then the page number. Need not mention ISSN number. Okay, you need not mention ISSN number. So like this format, you have to write the references. So now come to the last stage, that is the case study, that is experimental analysis. Now this case study, again you have abstract. How should be the abstract, you just see. So for my work, I have drawn this particular abstract like this. Presently, the refrigeration air conditioning industry searching for the alternative to R22 in terms of this is the basic introduction. What we have discussed in the second section, that is the orientation of that report. So basic introduction, and then what is that second para, you can see here the experimental and simulation methodology. So what method I have adopted, that also is there, and third one you can see the sample results. So result also you can see here, R32 having high latent heat, that is 337 kilojoule per kg, and 36%, 29.3% higher than COP, something is mentioned. So what do you mean? This abstract itself describes this research work related to refrigeration air conditioning, particularly by using R22 refrigerant to be eliminated from the vapor compression system because of the some environmental issues. Other alternative are searching. For that, the experimentation, second para, experimentation and simulation methodology has been adopted. You can see here IMR format. IMR, basic introduction, then methodology, and then the sample result also. You can see 3 para wise. And then the introduction, anyhow the introduction, what is air conditioning system, what are the various refrigerants, and then types of refrigerant, what are the basic components involved in that. Okay, and then their ODS reduction, and then their some comparison, the properties, and then the that is the basic introduction. Already we have discussed. It should be there. It should not exceed in between the range of 8 to 12. Then coming to literature review, regarding literature review, already we have discussed. You can see that the orientation of the literature review. The purpose of this chapter is to provide with insight into the development of refrigeration and air conditioning system for the era of discovery of the natural ice to the today's modern days. Some overview is written here and followed by the authors, previous researchers explanation, and their experimentation, their observation has been described here in the form of quantitative and qualitative presentation. So then the summary of the literature, you need to summarize the literature, and then gaps identification. So if you can see here, how many gaps are, 6 gaps are there. Generally 3 to 4 gaps is enough, but I have mentioned 2 to 6 gaps. And then the problem formulation, as we have discussed the problem statement. The aim of this research work is experimental investigation and performance comparison of zero ODP HFC hydrofluorocarbon group refrigerant in an air conditioning system. Simple statement. Okay, that itself gives the clarity for the experts, those who are going to review your work. And then objectives. So objectives always you start with the two statement. What is that? To investigate, to compare, and then to analyze, to validate, to model. Like that you have to mention. So if you can see first objective here, to investigate the performance characteristics of the window air conditioning system of a vapor compression refrigeration cycle with the selected 3 refrigerant. So what it is? So this particular research carries out with 3 refrigerant of the performance. Then what is that? Investigation of performance carried on window air conditioner. Second one is the to compare the thermodynamic and transport properties. What would be the parameters? What is the boiling point of the refrigerant, freezing point of the refrigerant, operating pressures, coefficient of performance, and the work done, and latent heat of vaporization, specific volume, all sort of parameters to be required. That is nothing but that comes under the data collection where we have previously discussed. Then third one, to compare the performance parameter. Then what should I do with the mass flow rate, coefficient of performance, cooling capacity, pressure ratio, energy efficiency ratio, power consumption. So like that, so the objectives should be mentioned. And again, flow chart, what we have discussed, the flow chart previously also same. And then the model vapor compression system, where you can see the compressor, condenser, expansion valve, and evaporator. And then the system computation, very important role. As a engineer, that too, the research in mechanical engineering definitely involves the mathematical computation. You have to compute and analyze the parameters which are involved in the analysis, and at the end you have to come one idea that suppose COP is reducing. To reduce the COP, what are the consequences of that closed cycle? Okay, if that refrigerant is properly flowing through the system, our net refrigeration effect is not up to the mark, the work done by the compressor is low, more and more power is consumption is taking place. So then you need to check that one. Then the pressure ratio, the condenser pressure to the evaporator pressure as well, the parameters you can discuss. So here, and also the system design consideration, how should be the system design. And then that previous chapter is related to the experimental analysis. Then same thing, so in simulation also we can give as a input parameter, and we can analyze these properties: pressure, density, volume, enthalpy, like this. So I have used on the cool pack simulation, where you can see here the vapor compression system for simulation. So of course, the compared to experimentation, the simulation is less risky and low cost. So experimentation, you have to purchase material, you have to fabricate, and you have to run the experiment once or twice or more than 10 times as well. So it is time involved and then cost involved. So most of the students, what they do, the simulation work. So if you can see here that if you the cyclic analysis of one stage cycle, if you give any input parameter here, the mass flow rate I have given 0.493 kg per second with the operating temperature of so 54.5 condenser temperature, and evaporator temperature is 7.2 degrees Celsius. So to be maintained my evaporator temperature at 7.2 degrees Celsius with this mass flow rate, what is the cooling effect produced? So I need to analyze the system performance. So what is that operating temperature of condenser? 54.5. So with respect to that amount of heat rejected from the cycle, also you can compute. At the end you can see the coefficient of performance, COP is 2.537. Okay, so for that given input parameters, the COP obtained is 2.537 is the COP. So like that, the input parameters where you can see is the TE 7.2 degrees Celsius, TC 54 point. So I have given these are the two input parameters with the mass flow rate. You have to select the refrigerant here. This is a simulation tool. So whatever refrigerant you want, you can select, and whatever temperature range you can select. Ultimately, it gives the coefficient of performance. So for this, if you go for experimentation, as we have discussed, it is lot of cost and the time involved. So most of the it is better than you can run. Better means we cannot say the simulation study give the 100% accurate. Sometimes maybe experimental error also would be there. Then we need to consider. So analysis of compressor performance. So and then so the calorimeter test, various components. Why? Because experimentation, no, various components involved in this particular study. And then the comparison with thermocouples. So this is the hermetically sealed compressor. All the thermocouples wherever required at top of the compressor, middle of the compressor, and bottom of the compressor. So the thermocouples are incorporated so that each and every level the temperature we can see. Then ultimately, so the inside the motor winding temperature also we have to analyze. Then measurements, and then results. So results and discussion plays very important role. Why? Because you have run that vapor compression system both in simulation and experimental. How those results are predicted and what is the trend of the plots. Mostly result and discussion section should be described with the plots, graphs, and the table. So you need to compare in the table the various parameters. You need to highlight those parameters in the form of the graphs, a trend of the plot, or how increasing decreasing fashion that you can also explain. So you can see in the second plot, so all the plots are showing the negative trend here. So why it is so, you have to justify that. Then also you can see that the curvilinear problem graphs, as well as the increasing order graph, the trend of the plot increasing decreasing you have to discuss. And then the each and every parameter, what is contribution of that pressure ratio and different condenser and evaporator temperature, so you need to discuss. So these are the various comparison. And then already we have discussed the what is that results and discussion should have plots, table, and as well as the graphs. So if we see here table, one particular simulated results, what is that? We are comparing three types of refrigerant, R22, 410A, R32. Then it's three cooling capacities in kilowatt. Again, the mass flow rate. With respect to mass flow rate, how the cooling capacity is varying of those three selected refrigerant, and also the performance of those three selected refrigerant as well. The variation of refrigerant effect, mass flow rate. So this how you need to explain and draw the RN results and discussion chapter. So next, I'll skip this too many PPTs. So at the end, you can see that chapter 7, conclusions and scope for future work. So concluding remarks, the following conclusions have been drawn after the comparison of both the simulated and experimental results. Then what is the first conclusion? R32 is the most balanced solution, not depleting the ozone layer. Okay, like that you have to mention. Second one is then ideal refrigerant should have the high latent rate of vaporization. So like that, so based on the uh, observe objectives you have fixed, you have to draw the conclusion. So at the end, what I can say, the uh, uh, so the GOC, identification of objective fixing, C for conclusion. Thank you very much, Madhukar.
Sir, hello?
Thank you, sir.
Ah,
Uh,
okay.
I request all our participants, if you have any queries, please you can go ahead.
If anyone on the part have any doubts, you can unmute and ask.
Participants. If no, we'll conclude it here.
Any participants are there, please you can ask.
Okay.
Wait.
Thank you, sir.
Okay, thank you very much. The lots management and all the principal, HOD, and then the coordinators. Thank you, one and all, and also more importantly, participants. Thank you, one and all.
Thank you, sir. Sir,
Thank you,
please,
sir. We appreciate your time and effort in delivering such an informative session. Your session was truly enlightening, and we are grateful for your contribution to our learning. With this, we conclude this, and we'll go for a vote of thanks. It's an honor to deliver the vote of thanks today on behalf of the organizing team, Lord's Institute of Engineering Technology, Department of Mechanical Engineering. I sincerely thank our chief guest for their inspiring presence and valuable words. A big thank you to all our speakers, guests, and participants for making this event meaningful and engaging. Special thanks to our organizers and volunteers whose hard work made everything run smoothly. And of course, a heartfelt thanks to our wonderful audience for your time and support. Thank you all. We'll meet you again tomorrow, third day session. Thank you again.